Tyler's cooking. But I like the crispy crust. Well, there's burnt and there's blackened.
Oh, they just have
Blackened
have
is
to
burnt in.
see.
So we'll see. We'll judge his cooking when we get there. Oh, great. Well, I like to do a great thing. They can't grab it over so. Now, if I could get my wife to ever say that, that would be great. You're right. Yes. Good morning, ladies and gentlemen. How are we doing today? Good. A lot of those electronic devices that are out, please put them away. All of them, put them away. Take out your computers, ladies and gentlemen. We need to get through a little bit of stuff from yesterday and then talk about EMR and waves today. So let's get going. All right. Wow. All right, ladies and gentlemen. Yesterday we took and started watching a video, ladies and gentlemen. So we will finish watching that today. Sorry. There you go, sir. Okay. So, all right. So at the end of the hour yesterday, we were watching a video about an incident that happened at a nuclear reactor in the United States. It was at a place called 3 Mile Island, which is in Pennsylvania. Actually, there used to be the Pittsburgh Pirates used to play at 3 Mile Island Park in Pennsylvania. And again, an incident where there was some radioactive water vapor released into the air. And radiation levels were high. So let's finish watching that, ladies and gentlemen, and then we'll take and talk about it a little bit and move on to something else today on waves and EMR. So this is where we were kind of left off. Not an exact spot, ladies and gentlemen, but we were right here on the Saturday Night Live skit. Okay. So again, ladies and gentlemen, um, one of the things about energy is that any form of energy brings with it certain drawbacks. Okay. Um, what is the problem with wind energy?
Not always windy.
Right?
Not always windy.
Not always windy. What else is the problem with wind energy?
You can't control it.
You can't. Agreed. So it's not always windy. The other thing is, people don't like looking at fields of wind turbines in their backyards. It's really an issue. And where my parents lived, they put in wind turbines, and there were people who actually complained enough, and WPS, or the company that put them in, had to buy their houses because they claimed they were loud, they were noisy, there were other problems with it too. So, again, let's begin by saying this. Even if they put up lots of wind turbines everywhere, we are not getting enough energy from wind to power everything that everybody needs. Solar energy is another option. The problem with solar energy is, number one, you don't get a great deal of it from sources. You get enough to use as kind of a backup, kind of a secondary, and you cannot store solar energy in anything other than batteries now. And it isn't the most efficient system. So those are some downfalls for those things. The other way we've been making energy for years is we burn coal. What's the problem with burning coal?
Fossil fuels.
Fossil fuels. Anytime you burn something, ladies and gentlemen, you are going to release into the environment carbon dioxide gas. That happens anytime you burn things. And if you release too much carbon dioxide gas into the environment, it creates what we call the greenhouse effect, which is it traps heat near the surface of the earth. Now that may sound like a great idea. Oh, if it were warmer, that would be great, right? But it's not good for the polar caps at the north and the south pole of the planet. It's making those smaller, which means there's more water on the planet, which is a bad thing because if you live near water and the water level rises, you may someday be underwater. Nuclear power is the cleanest burning energy that we are going to get. There is nothing giving off during a nuclear reaction that is hazardous to the environment. All it is given off is heat. But the one drawback to nuclear energy, or the two drawbacks to nuclear energy, is number one, it creates waste. Not waste that go up into the environment, but waste that need to be stored somewhere because they stay radioactive for thousands of years. And number two, if a coal-burning power plant were to be struck by a natural disaster, an earthquake, things like that, they would simply shut it off. Worst case scenario, the coal in it would continue to burn for a little while. Well, when a nuclear reactor hits a disaster, it takes out a lot of things. The one at 3 Mile Island was very minor. No lives lost, no devastation. People still live in that area. The one that happened in Chernobyl, Russia, that is still a ghost town. The one that happened 13 years ago in Japan, that area is still uninhabitable. People cannot live there even if they wanted to because the radiation levels are too high. And that creates a problem for us, ladies and gentlemen, in that, yes, while it is a clean way of generating energy, while it is in a way that doesn't create a ton of waste, it is a way that is dangerous. And if something bad happens, you are talking about wiping out tens of thousands of people, if not more. So for a long time, the government put a hold on building any nuclear power plants. And it was only in the last few years that they've actually started to construct some more. All right, if you would open up your EISN to slide number 4, ladies and gentlemen. We've got a few notes to get through. We will get through those. I will give you time to work on this worksheet here, waves and EMR, or electromagnetic radiation. And then that'll be it. We'll be done with the day before we know it, ladies and gentlemen. All right. Electromagnetic radiation is specifically what we call radiation. Okay, that is the name of it. It is a form of energy. We studied it earlier this year when we talked about other forms of energy, like thermal and like nuclear and things like that. It gives off radiation. Now, radiation is all around us, ladies and gentlemen. Lights give off radiation. Okay? Radio and TV waves are radiation. Radiation is simply energy traveling as a wave. Energy moving from one place to another through a wave. Here we're looking at the different kinds of electromagnetic radiation, ladies and gentlemen. These are the kinds of it. The first is radio and TV waves. Now, we don't use these a lot anymore. Used to be you would turn your stereo in your car to a channel, and we still do broadcast radio stations. But most of you guys get your music through what?
Phone.
And what?
Phone is infrared.
Well, what I meant is a what on the phone? Normally an app, right?
Yeah.
Pandora, things like that, okay? Well, years ago, you used to have to tune your radio to station 101.1. That was what the WIXX was on. Now, it still is there, but there's not as many people who do that. Thank you.
Thank you.
Okay. Okay. All right. So radio and TV waves aren't used anymore, but what is taking their place now? What device do we have that still works on that form of electromagnetic radiation? What? Nope. Your cell phones. Cell phones work on radio and TV waves. Okay? Same frequency, basically, ladies and gentlemen. We move a little over and we get to something called microwaves. And we all know what those are. We all probably have one in our home. What's the purpose of the microwave in your home?
To heat up food.
How?
With using heat waves.
Nope, does not use heat waves. You touch the inside of your microwave, it is not hot after you've run it for minutes. It does use radiation, but what specifically does it do to food? Anybody know?
Makes particles move faster.
Specifically, water particles. Okay? Anybody watch the Batman movies when they came out with Christian Bale? No? Okay, never mind. Anyway, ladies and gentlemen, microwaves will cause water particles, water molecules in food to move faster. Okay? Will cause them to move faster, ladies and gentlemen. That heats up the food from the inside. Now, somebody asks me, well, how come the food's always cold in the middle? Why? Because it heats up the water particles that it gets to first. The ones in the middle take longer to heat up. Now, your remote controls in your home, those are infrared. Okay? Those are infrared. And when I was a kid, I remember the greatest day of my life when I was a kid, ladies and gentlemen, is the day we got cable TV. They put a box on top of my TV that I could get more than 3 channels out of. Okay? Not only that, but because they put a box on my TV, I had a remote control finally. When I was a kid, you had to walk up to the TV and turn a dial to change the channel. My grandpa used to sit about this far away from the TV during the day to watch his soap operas because he could reach over and he could change the channel that way. Yes?
When I was a kid, my grandparents still had that kind of TV, so whenever I would go visit them, they would actually make me run up and go.
Yep. Normally the youngest kid in the family was the remote control. Hey, Johnny, go change the channel to channel 5. Okay? But the greatest day was when we got cable TV. Because I had a box, I had a remote, I could turn the sound up, down, I could switch channel, I could turn it on and off. Didn't have to get up. But my mom had this habit of when it was your birthday, and you would get birthday cards from different family members, she would take and put them on top of the TV. Our TVs were what they called console TVs. They were like a big box, a big piece of furniture. You could put things on. So she would put all the different cards on top of the TV. Well, that was when I learned a very valuable lesson. Infrared remotes are not very strong signal. Because literally, if she put a card in front of where the receiver was on the cable box, you couldn't change the channel anymore. Now you had to go back and get up to move the card. The signal was blocked by a simple piece of paper. A piece of cardboard stopped the signal from being able to change the channel. Okay? Then we get into visible light, ladies and gentlemen, the light that we see above our heads. Now that light is actually made up of what? What? Nope. Nope. What colors is it made up of?
Roy G. Biv.
Roy G. Biv. Anybody know what Roy G. Biv stands for?
Red,
Roy.
orange. Yeah.
Red, orange.
Yellow.
What's
Indigo.
Green, blue.
yellow, green, blue, indigo, violet? Roy, red, orange, yellow. G, green. Biv, blue, indigo, violet. Those colors. Violet, purple. Okay? So when that light comes and hits Hassan's shirt, Hassan's shirt absorbs all of the colors of light except for one, blue. And it reflects it back at us, and we see the blue light coming off of his shirt. Okay? Now Savannah has on a red sweatshirt. White light hits it, it absorbs orange, yellow, green, indigo, blue, violet, but it reflects the red. Jeremiah's shirt is black. It absorbs every color. And what we're actually seeing in his black shirt is the absence of light being reflected to us. But when you look at something that is white, white reflects them all. White reflects them all. Which is why in summer, if you want to be cooler, they will tell you to wear what?
White.
Wear white. Don't wear black. Black is going to absorb more energy. Black is going to make you hotter. White will reflect it. It will actually, you will be cooler wearing a white shirt in summer than you will wearing a black. All right, what's ultraviolet light do? What does it do for you?
It can give you cancer, but it's reflected in sunlight.
It is part of sunlight. It can cause cancer for some people. But what does it do to most people if you're out in the sun too long? Tan or a sunburn. Now I want you to think about this for a minute. An unexpected color change is a sign of what kind of change? Chemical change, chemical reaction. So when sunlight hits your skin and the ultraviolet light penetrates your skin, it causes it to change color. Hey, that's a chemical reaction, ladies and gentlemen. That is a chemical reaction actually changing part of the cells of your skin. That is why for some people they end up getting skin cancer, because that reaction turns into a mutation. Okay? So again, ultraviolet, a lot stronger than infrared and the others. All right, what will an X-ray do?
You can see through tissue.
You can see through skin. You can see through tissue. You can see through muscle. What can't you see through?
The bones.
Bone. So guess what? If an X-ray hits your arm, what does it do to all of those things? Muscle, tissue, skin.
Penetrate.
Goes right through them. Right through them. What does the person who's taking the X-ray do when you go get an X-ray? They leave the room.
I'll be doing that someday.
Okay? Years ago, they didn't have you leave the room.
Yeah.
Years ago, they didn't know it was harmful. They thought it was the greatest thing to be able to see inside the body with an X-ray. They didn't realize it was harming the X-ray technicians. Why? Because they were there 5 days a week, 8 hours a day, taking X-rays. They were being exposed to high levels of radiation. We didn't know it at the time. Now they ask you to step outside. What do they do to you if you're being X-rayed?
Put something like a drape over you. I think it's
Yeah, kind of light, right?
Yeah.
No.
It's like lead.
It has lead in it. It has lead in it so that you don't get the rest of your body exposed to those X-rays. We only want to expose the part of your body that we need to. Why? It's going through everything except for bone. Okay? And then there are gamma rays, which are even stronger than X-rays. Now, what are gamma rays good for? Really?
I can only think of comic book books.
Yeah, what's it do?
You can see through the.
No, it makes you into a
Yeah.
beast that when you get angry, you get incredibly strong, you turn green, and you can throw things around.
I know, but
The Incredible Hulk, right?
yeah, I'm trying to think of real life examples.
There aren't. Well, there are. Gamma rays can be used as radiation treatment to kill cancer cells.
Yeah.
To kill cancer cells. The problem is gamma rays don't distinguish. What do we mean by that? Whatever cells they come in contact with, they will kill. But the advantage of killing off the cancer cells is worth the fact that it kills off some healthy cells as well. These are all different forms of electromagnetic radiation, ladies and gentlemen. Okay? Now, in terms of wave, this energy traveling as wave, go ahead, Keanu.
I was gonna say, is that why a lot of like cancer patients who are on like chemotherapy tend to be like a lot weaker and get sick?
And one of the big things that it kills are white blood cells in the body that are responsible for what?
Health protecting.
Yeah, your immunization system. So if you get a cold or things like that, white blood cells go and attack viruses and things like that. When you take some of those white blood cells out of the body, it makes you more susceptible to illnesses. There are two kinds of waves, ladies and gentlemen. There is a longitudinal wave. Longitudinal wave is a wave that says, okay, we're going to be like a spring, and we're going to compress the spring, and then we're going to pull the spring apart. That is a longitudinal wave. And then there is a transverse wave. That is like a water wave. A wave in the water where it moves up and down, or a wave in a stadium where you move up and down, right? You stand up, wave your arms, sit back down. But what don't you do when you're doing the wave in the stadium? No, well, you don't. But you also don't what? As the wave goes around the stadium,
Keep going.
you don't move with it, do you? Your movement is stand up, wave your hands, sit down. Think of how great it would be if you got to move with the wave and you got to the 50-yard line and you're like, I'm good, I'm stopping here. Okay? I had end zone seats before, now I'm at the 50-yard line. That'd be great, right? Okay? That doesn't happen though. The particles move up and down. The particles don't move with the wave. They don't. All right. The other kind, that would be a transverse, ladies and gentlemen. All right. So, separate way of looking at waves. Mechanical and electromagnetic. Mechanical wave is a wave that requires a medium. Sound is a mechanical wave. What is the medium for sound? What does it travel through? The air. If there were no air in this room, you wouldn't hear a darn thing. Nothing. And this is a longitudinal wave, meaning my voice causes air particles to vibrate back and forth. They cause other particles to vibrate, and eventually they hit on the eardrum of your ear. And the beating of those particles on your ears, oh yeah, Mr. Brand is talking again. Okay? But you have to have something for them to travel through. That's what a medium is. Mediums can change your wave speed. What do you do when you go to a beach? After you lay your stuff out on the beach, when you were a little kid, what did you go and do right afterwards?
Sand.
Nope, not me. I went running into the water. Now, you ever try to run in water?
Yep.
Is it easy? No, why?
Water slows you down.
Yeah, because it slows you down. Guess what? It does the exact same thing to a wave. Traveling through air, the wave can move a lot faster. But when you get to water, because it's thicker, because it's more dense, it slows you down. Slows down the wave as well. Okay? Slows down the wave as well. Okay? So examples are a water wave, a stadium wave, a sound wave. Those are all mechanical waves. What we're talking about up there, ladies and gentlemen, are electromagnetic waves. Electromagnetic waves don't need anything to travel through, which is good because most of our electromagnetic waves come from the sun. The sun. And guess what? If they needed a medium to travel through, there is none between us and the sun. So they would never get here. But because electromagnetic waves do not need a medium, they can travel through empty space. They all travel at the same speed. Anybody know what the actual speed is? What? Speed of light, yes. Now here's what the speed of light is, ladies and gentlemen. This is 1 meter. Okay? Now imagine having 300 million of these end to end to end. Okay? And at one end, Jace turns on the light. 1 second later, you will see the light at the other end of the 300 million of these. That's how fast light travels. That's how fast all electromagnetic waves travel. Now think about that. 300 million of these in 1 second. 1 second. And yet the light we go outside and see this afternoon from the sun took 8.5 minutes to get here. 300 million of these every second. 8.5 minutes is how long it takes light from the sun to travel to get here. So if the sun burned out 7 minutes and 30 seconds ago, we'd have 1 minute of sunlight left. That's how long it takes to get here. But it is booking it. That speed is fast, ladies and gentlemen. That speed is fast. 3.00 times 10 to the 8th meters per second. Called the speed of light. Good. Examples of electromagnetic rays: X-rays, light, radio waves, microwaves. All right, a little bit about longitudinal waves. Now, it's hard to see, but where this darker spot is here, this is where the wave gets compressed, pushed together. Here, this is where it is more spread out, okay? It travels in an in and out or a back and forth manner. So if we were looking at it, it would be going this way and this way, okay? Rarefaction is the part of the wave where it is spread out. So imagine stretching a spring, okay? Then, ladies and gentlemen, there is the part where it is pushed together. They call that compression. Those are the two parts of a longitudinal wave, the rarefaction and the compression. Now, there's also something called amplitude. It is how compressed or how spread out the particles in a wave are. Now, in a sound wave, which is a little bit different, amplitude affects the
Sound, the
volume, which is why if you have an electric guitar, it may have an amplifier to amplify that sound. But in a transverse wave, like we were just talking about, okay, that is a wave that travels in an up and down manner. And now you have the high point of a wave called the crest. This is what we're used to seeing. This is what we would see in water. The low point is called the trough. The amplitude is 1/2 of the total height from the crest down to the trough, or this line they call a normal, which is right in the middle of the wave. From there to the crest or there to the trough, that is the amplitude. And again, in a sound wave, this is what you amplify to make it louder. All right, this is what you amplify to make it louder. All right? All right. Some things that all waves have in property. There is a certain wavelength. That is the distance of one complete wave. Okay? Now, for electromagnetic radiation, even though they all travel at the same speed, their wavelengths are very different from one side to the other. And I'll show you an example on the next slide. But wavelength is how long the waves are. Okay, the distance of one complete wave. From compression to compression, from trough to trough, however you want to describe it. One complete wave. Rarefaction to rarefaction, crest to crest, doesn't matter. One complete wave. And it is measured in nanometers. Now, nano is 1 × 10 to the -9th meter. That is, millimeter is 10 to the -3rd. Micrometer is 10 to the -6th. This is 1/100000th of a meter. 1/10000000th. Okay? Frequency is how often something happens. So in waves, it's the number of waves that pass a point in a given second. And when you're tuning your radio to star 98, you are tuning to a certain frequency of wavelength so you can convert that into the sound we hear coming through our radios. Okay? The unit for frequency is called hertz. Hertz is the unit for frequency. Okay? All right. So this is where I was going to show you this. For a radio and TV wave, they are literally about 1,000 meters long. 1,000 meters long. That is pretty long, right? Okay. For microwave, they are about a centimeter. Okay. When you get to infrared, they are about 10 micrometers. A lot smaller. And then we just keep getting smaller and smaller and smaller. To give you a reference point, radio waves are as big as buildings. Microwaves are as big as a honeybee. Infrared is like the point on a pin. Visible light is like bacteria and protozoa. Ultraviolet, the size of molecules. X-ray, the size of an atom. And gamma, the size of the nucleus of an atom. So they get to the point where they're incredibly tiny. Okay? Now, so what is happening to wavelength as we go across this, though? It's getting what?
Goes from small to big. Well, like closer.
Goes from big to small. Long wavelength here, short there. That's why they get closer together. Okay? Frequency we will talk about in a minute. We're not going to worry about temperature. But look up here. Our atmosphere only allows certain wavelengths of light, of energy to get through. Which two can get through?
Visible light.
And what's the other one?
Radio.
Radio and TV waves. It's a good thing our atmosphere lets those through. Why? Otherwise, we would have no light from the sun. And without radio and TV waves, what wouldn't we be able to communicate with? Why? Actually, we would. Phones, we would.
Wireless phones.
What?
Wireless phones?
No, your cell phones would still work because where does your cell phone get its signal from?
Towers.
Towers on your surface, right? But what's out in space that we need to get a signal to occasionally?
Satellites.
What?
Satellites.
Yeah, we would have no GPS on our phones if it could not send a signal out into space and get it back. Our atmosphere blocks ultraviolet, X-rays, and gamma rays. At least most ultraviolet, if you do get through. Our atmosphere blocks microwaves and infrared, which is a good thing because these are the things that are harmful to us. These over here. And our atmosphere blocks them out so they can't get to us. Okay? So that is a good thing, ladies and gentlemen. All right. So here it is. Relationships. Final slide. Yes, go ahead.
Okay. So what if for like half of a second the atmosphere like disappeared and then reappeared and like people were outside? What would happen to them?
For a short period of time like that, I don't know if they would be exposed to enough radiation. It's possible that they could get enough radiation damage and die, but I don't know for sure. I do know this. When you talk about astronauts who are in space, they need to be protected from those things because they do not have the atmosphere protecting them. So space suits and space shuttles and things like that are designed to keep out that radiation that would get to them otherwise. Now, again, you can't do it. You can't step out into space without a spacesuit on anyway. But if you could, you would be exposed to high levels of radiation, and that would be bad for you. Extremely. All right. So just like in the last unit, we're going to look at relationships here between these three things: energy, frequency, and wavelength. So if the wavelength goes down, frequency goes up. What kind of relationship? Inverse. If the wavelength goes down, energy goes up. What kind of relationship? Inverse. And then finally, if frequency goes up, energy goes up. That would be a direct. So really, ladies and gentlemen, the longer the wave, okay, the longer the wave, the less the frequency, the lower the energy. Radio and TV waves, microwaves, infrared, probably not harmful to us. But when you decrease the wavelength, you're exposed to a lot more waves. The frequency is higher and the energy is higher, ladies and gentlemen. And that is when it can be more dangerous. Questions? All right, that is the last slide that I have for you for today, ladies and gentlemen. You have got about 18, 19 minutes left. There's a worksheet there that you can get to work on. You can use these notes as help to get that done, ladies and gentlemen. And that will be the last thing that I have for you today. So if you would, ladies and gentlemen, go to work on that worksheet. And if you have questions, you can let me know.
Mr. Brown,
Yes.
are you gonna take this back or can I recycle it?
You can recycle it or whatever you would like to do. It's yours.
What is it?
Well, in about 5 minutes, they're going to be calling you down to the cafeteria. If you get one of these to whatever the Red Devil Pride reward is.
Okay.
So if you earned a Red Devil Pride by being or having 85% or greater attendance, no tardies, no major referrals, there's some kind of reward that they're going to be giving you today before you leave. I don't know what it is. They have not told us. So they just said to fill it out from the list they gave us, hand them out, and listen for the announcements.